This is the factorial. It's a function you're very likely already familiar with. The factorial of a positive integer n is just the product of n with all positive integers less than it. But what happens if we take the exclamation point of the factorial and put it on the left side of n? Does this wacky expression mean anything? The answer is yes, but to explain it, we'll first require a dark room containing several men without their hats. So let's say we have this room and there are several men in this room. For brevity, let's just say there are 3 men in this room. They are partying, they are having a great time and yucking it up. And let's say by the entryway, we have a hat rack and they have hung their hats on this rack as they entered the room to party. Perhaps this is man 1, this is man 2, and this is man 3, and we'll label their hats accordingly. There's hat 1, there's hat 2, and there is hat 3. Now, just as they're ready to leave the party, a storm is brewing outside, and by brewing, I mean raging. It's raining and lightning is striking down like Zeus's fury has been unleashed upon them, and the power goes out. The room is black as night. They can't see a thing. In particular, they can't see the numbers conveniently written upon their hats. So then we are in this treacherous situation. We have 3 hats and 3 men who cannot see which hat is theirs. Perhaps they start to take their hats, and man 2 takes hat 1, man 1 takes hat 3, and man 3 takes hat 2. Not a single man has gotten his hat back. Our question is, how many ways can this happen that no man gets the correct hat back? In this case, with just 3 men and 3 hats, there are actually only 2 ways this could happen. The other way would be that man 3 takes hat 1, man 1 takes hat 2, and man 2 takes hat 3. So in this case, there are 2 ways that the 3 men could not get any of the correct hats back. These ways of shuffling objects around so that no object goes where it's supposed to is called a derangement. And this is where the exclamation point on the left comes in. We've just found that the number of derangements of the number 3, which is written with an exclamation point on the left, is equal to 2. And this is called a subfactorial. It counts the number of derangements of 3 objects in this case. Well, it was fairly quick to see that there are 2 derangements of 3 objects. Larger examples will quickly become quite difficult, and so a general formula would be desired. Let's say we use numbers both to represent men and the hats that belong to them. So hat 1 belongs to man 1, hat 2 belongs to man 2, and so on. Then we could look at this notation as representing a way of giving hats back to men. In this way, we see that hat 1 is given to man 1, hat 2 is given to man 3, hat 3 is given to man 2, and hat 4 is given to man 4. This is a common notation to write out what is called a permutation. It is effectively an ordering of the hats. Now, in this case, this is not one of the orderings of hats that we're trying to count. Remember, we're thinking about how many ways we can give the hats back to the men so that nobody gets the correct hat. We see that in this case, man 1 got the correct hat back, and man 4 got the correct hat back. These are called fixed points. Hat 1 stayed with man 1, hat 4 stayed with man 4. They are fixed hats, or more generally, like I said, fixed points. And one last bit of notation to strip all the soul from this problem. We're representing the hats with numbers 1 through 4. If we had 8 hats, we'd use 1 through 8. There's a convenient symbol for sets like that, and it's with a square bracket with n inside. This is just a nice way of representing the set of all positive integers 1 up through n. So, while the subfactorial of a positive integer n can be viewed as the number of ways we could give n men their hats back so that none of them get the correct hat, A more mathematical way to phrase the question is like this: how many permutations of the set of the first n positive integers have no fixed points? A permutation of this set of n integers shuffles the integers around, but it might not necessarily shuffle all of them around. Some of them may be left in place as fixed points. And so, to compute a subfactorial, we need to count how many permutations leave no fixed points. How many permutations are there on a set of n integers such that every single integer is moved around? I hope you can appreciate the humor in the juxtaposition between the hat problem and this more mathematical phrasing, but we will bring it back to the hats once we've answered this question to answer this final, shocking question, which is how likely is it that nobody gets their hat back? And this one will blow your socks off. Now, thankfully for us, we already know the number of permutations there are on the set of the first n positive integers, that is, n factorial, because if we're shuffling the integers around, we would have n choices for which integer goes first, n minus 1 choices left for which integer goes second, and so on. It is n factorial. So this counts all the permutations. Again, we want to know how many permutations have no fixed points. So to count that, the strategy we're going to use is to take n factorial, the number of all permutations, and then subtract the number of permutations that have at least one fixed point. If we count up all permutations and then take away the ones that have at least one fixed point, naturally we will be left with exactly the number of permutations that have no fixed points, which is the subfactorial of n. So we're going to have to start naming some sets to make this work. We're going to let AI be the set of all permutations where I is fixed. So for example, this permutation, which sends 1 to 1, 2 to 3, 3 to 4, and 4 to 2, this would belong to A1, because this is a permutation that leaves the element 1 fixed. 1 gets sent to itself. It is fixed. All the other elements happen to move around, but since 1 is fixed, this would be in A1. Just for the example, I've used 4 elements here, but keep in mind our discussion is about the set of n positive integers in general, so the argument will apply in all cases. So a permutation like this would be in A1, but in general, if we're talking about permutations on the set of the first n positive integers, how many permutations total would be in A1? How many permutations are there that leave 1 fixed? This symbol represents the number of elements in the set. Well, since every permutation in A1 has to have 1 fixed, 1 is the only element that's not allowed to move. If there's n elements total, there are n minus 1 other elements, and those can be ordered freely. Hence, there are n minus 1 factorial permutations, which will leave 1 fixed, and of course those other n minus 1 elements are allowed to be moved freely. The same argument would show that the number of permutations leaving any element I fixed is n minus 1 factorial, because that one element I has to be fixed, but all of the other n minus 1 elements can be permuted freely. That's how we get n minus 1 factorial. So how many permutations have at least one fixed point? Well, we may think it is this, the sum of the numbers of permutations that are in all of these sets A1 through AN. However, this count is not correct. It has a big problem. And that problem is double counting. Consider a permutation like this, that sends 1 to 1, 2 to 3, 3 to 2, and 4 to 4. A permutation like this does have 1 as a fixed point, and so it would belong to A1. But it also has 4 as a fixed point, so it would also belong to A4. So in this sum, a permutation like this would get counted twice. It would get counted once for each of its fixed points. The fixed point of 1 makes it counted here, and the fixed point of 4 would make it counted in the number of elements that are in A4. And this applies to every permutation that has 2 fixed points. It would appear once in the count for each of its fixed points. They've all been double counted, and so we need to subtract all of those permutations that have 2 fixed points to correct this. To help us figure out exactly what we need to subtract, first consider this: how many permutations are in the intersection of A1 with A2? This would be all of the permutations that have 1 fixed and 2 fixed. Well, we can use similar logic to what we used before. If these are the permutations that have both 1 and 2 fixed, well, the number of ways we could do that is n minus 2 factorial, because 1 is fixed and 2 is fixed, but the other n minus 2 elements can be permuted freely. So the number of permutations in this intersection would be n minus 2 factorial. Again, this represents the permutations in A1 and in A2, which means that they leave both 1 and 2 fixed. But of course, we can't just subtract this from this sum. What we actually need to subtract is the sum of the numbers of elements in all intersections of this kind. That is, the sum of the numbers of permutations in all intersections AI with AJ. Because a permutation that leaves 1 and 2 fixed will be counted twice, so we need to correct for that, but so will a permutation that leaves 1 and 3 fixed, or 1 and 4 fixed. Every single intersection like this, with I not equal to j, needs to be counted up. Thankfully, adding all of this up is not a difficult thing. For every intersection, the number of permutations it will have will follow the same logic as before. It's going to be n minus 2 factorial. So then the question is just, how many of these two-way intersections are there? The answer to that question is a binomial coefficient, n choose 2. I'll leave a link in the description to my lesson going over this symbol and how it's calculated. It is read n choose 2. In this case, it's the number of ways we can choose 2 sets from our collection of n of them. So we will have n choose 2 of these two-way intersections, and every one of them will have n minus 2 factorial permutations. Unfortunately, simply subtracting this from the count we had before is not going to be enough. The problem goes deeper still. We've now addressed the problem for permutations that have 2 fixed points, but any permutation with 3 fixed points is going to be counted 3 times in this sum, but then it would be subtracted 3 times in this sum, so we would be left not counting them at all, which means we need to add those 3-way intersections back in. However, once we do that, any permutation with 4 fixed points will have now been double counted, and so we would then need to subtract all of the 4-way intersections to correct for that. This problem continues, but thankfully there is a nice formula for calculations like this. It's called the inclusion-exclusion principle. Link in the description to my video talking about that. We definitely need to use it here. This big ugly formula is the inclusion-exclusion principle. In our case, what we have on the left is the number of permutations that are in all of these sets A1 through AN put together. So these are just all of the permutations that have at least 1 fixed point. How do we count them? Well, that's the expression on the right. Without going into the details of this notation too much, it is just describing the pattern we've already seen. We see that j starts at 1 and will count up to n. That's going to cause this -1 to alternate between positive and negative. When j equals 1, this is -1 to the 0, so it would just be +1. That's why we are adding terms at the start. The other thing that j is doing is increasing the sizes of these intersections. We start with adding the one-way intersections, which aren't intersections at all, and then we move on to subtracting the two-way intersections, then adding the 3 ways, subtracting the 4 ways, and so on until we get to n. And that's exactly what we just walked through. Add up the 1 ways, then we were talking about subtracting the 2 ways, then adding the 3 ways, and so on. While the expression on the right does not look too nice, in our case, it is rather easy to calculate. We said how any single set, A1, A2, or A3, would necessarily have n minus 1 factorial permutations in it, because if one element is required to be fixed, then it's n minus 1 other elements that can be permuted freely. Now, how many single sets do we have like that? Well, that would just be n choose 1. For example, the set A2 has the element 2 fixed, and thus contains n minus 1 factorial permutations, where 2 is fixed and the other elements can be permuted freely, and since we have n sets, that's what this is. N choose 1 is just n, it's multiplying this by the n sets we have. We then get on to the case of the two-way intersections which need to be subtracted. Like we said, we have n minus 2 factorial permutations in each of those two-way intersections, and the total number of two-way intersections is n choose 2, the number of ways we can choose two sets from our total of n. We then have to add the number of permutations in the three-way intersections. Each one of those intersections would have n minus 3 factorial permutations, because 3 elements can't be moved, but the other n minus 3 elements can be permuted freely. And of course, the number of those intersections we would have is n choose 3, the number of ways to choose 3 sets from a collection of n. And this pattern continues. So we see the signs alternate, positive, negative, and so on, but every term in this count has the same exact form. That form is n choose I multiplied by n minus I factorial. If you've seen our discussion on this, n choose I, then you know that it is equal to n factorial divided by n minus I factorial multiplied by I factorial. So that is that, and then of course it's still getting multiplied by n minus I factorial, and you see there is cancellation. This n minus I factorial cancels out with this one. Hence, every single term in that ugly sum we were looking at actually has the rather simple form n factorial over I factorial. So how many permutations are there with at least one fixed point? Well, we know that every single term of that expression has the form n factorial over I factorial, and we just need to alternate sign. So we'll throw in a -1 to the power of I minus 1, where I starts at 1 and goes up to n. This is counting up all permutations with at least one fixed point by the inclusion-exclusion principle and all the logic we previously went over. Since we know how many permutations have at least one fixed point, we're now prepared to calculate the subfactorial, the number of permutations with no fixed points. We know that this is the total number of permutations, n factorial, minus this number that have at least one fixed point. Rather than writing it as a sum in summation notation, let's just write the terms out. When I is equal to 1, we would have -1 to the I minus 1, which would just be 0 in that case, and we would be left with n factorial over 1 factorial, so just n factorial. Then when I equals 2, we would have minus n factorial divided by 2 factorial. Then we would have plus n factorial over 3 factorial, and so on. This would go until finally ending with plus or minus, depending on whether n is odd or even, n factorial divided by n factorial in that final case where I is equal to n. Then if we distribute this negative sign, this n factorial and that n factorial would cancel out, and then the signs of everything else would simply be flipped. This would thus end up being the sum of terms of the form n factorial divided by I factorial, where I starts at 2 and counts up to n, and we need to alternate sign, but we want to start with a positive. So we'll throw in a -1 to the power of I. I starts at 2, -1 to the 2 is positive, and from there it will just alternate between negative and positive. And in fact, if you wanted the index I to start at 0, you could just write it that way. The first terms would just cancel out. It would be n factorial minus n factorial. So we could write it like this with I starting at 0. But however we choose to write it, that's how to calculate n subfactorial, the number of ways that we can permute n positive integers so that none of them remain in place. That's the answer to this question, how many permutations have no fixed points. But now we're prepared to answer this question, how likely is it that nobody gets their hat back? Well, we need to take the number of ways that nobody could get their hat back and divide by the total number of ways the hats could be given back. So, in the numerator, we'll put the total number of ways that nobody could get their hat back, which is the stuff we just discussed. It's the subfactorial, which, expressed as a sum, is the sum from I equals 0 to n of -1 to the I multiplied by n factorial divided by I factorial. This is how many ways the hats can be given back, so nobody gets the right hat, and the total number of ways the hats can be given back is n factorial, if we have n men and n hats. Now, looking at this division, we see the n factorials actually cancel out, and so we're left with a very simple sigma. We have the sum from I equals 0 to n of -1 to the I divided by I factorial. So this is the probability. We take the number of ways that nobody could get their hat back and divide by the total number of ways the hats can be given back, and this is what we get, which, if we expand it, happens to be 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial, and so on. So that's the probability. But what the heck is this? Well, of course, this sum only goes up to plus or minus, depending on whether n is even or odd, plus or minus 1 over n factorial. It stops when I gets to n. So clearly it depends on the value of n. But to get a rough idea of what this probability is, we could ask what value does it approach as n gets really large. That's what this means, the limit of this sum as n approaches positive infinity. Well, depending on the value of n, this expression will equal different things, but as n gets arbitrarily large, this sum is actually going to get arbitrarily close to 1 divided by the transcendental number e. Those of you familiar with calculus may recognize this as the Maclaurin series for e to the x, with x equal to -1, and thus perhaps saw this result coming. But how about that? By taking a large group of men, shuffling their hats about, and turning the lights off, you are flirting with one of math's most legendary numbers. Now, of course, the actual decimal value of this may be of some interest to you. It is about 0.37, so that's over a third, which means for large n, there's a pretty good chance nobody gets the correct hat back in this situation. Now, in our work with the limit, we saw that n subfactorial divided by n factorial is very similar to 1 over e as n gets large. And so you may think, multiplying both sides by n factorial, that n subfactorial could be well estimated by n factorial divided by e. And in fact, this is the case. If you take n factorial divided by e and round this to the nearest integer, so I'll just write round of this, you actually will get n subfactorial. Let's take it all the way back to the beginning where we said that 3 subfactorial is equal to 2. Based on our work, we could have gotten that by dividing n factorial by e and then rounding. Well, let's see. 3 factorial is 3 times 2, so 3 times 2, we get 6, and if we divide that by e to the power of just 1, we get 2.207. If you round it, you get 2. So that's your subfactorial. I think it's pretty funny notation, and it's pretty amusing, both that it comes from a fun hat problem, or it can if you want it to, and I do, and that E shows up. It's always a fun day when E shows up. So let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Erase the tone of words and just how I say shit. And let me speak my poetry to your face. It's not in the mid if you ain't listening. Not infinite if you ain't really in it.